forget that. Hold. And we'll go from current slide. And I'll even turn on the projector. Okay. First thing I want to know, any questions from anything we've covered so far? Oh, yeah. And a few people might need to test. Okay. Pretty sure I've got a copy for you. Yes, here we go. Anyone else? Get a copy of the test. Okay. Let me ask you a question. You were engineering and now math, or is that right? Okay. Because I saw a list for you. It still had you engineering. And I thought maybe you didn't change, but it doesn't matter. We'll talk later if you want to. Okay. All right. Any questions? Anything we've covered so far? All right. We finished chapter 1. You got the test of chapter 1. If you finish it anytime, you can turn it in anytime. If you have questions anytime, please ask questions. I'll tell you one question I will answer it. Like, can you do number 3? And my answer will be yes, but I'm not going to, okay? Because the test questions, that's for me to evaluate how you're doing. If you want me to do something like number 3, or any one, I'll just pick 3 out of the air, then find one like it in the text, and I'll be glad to do anything from the book, as long as it's not identically the same as the one on your test. Okay, does that make sense? All right, good deal. So if you have any questions, please let me know. All right, if none, yes?
The first 2 questions, they seem like they're from chapter 2.
Oh, I forgot to do that. Let me find the test again. Okay. Hold on just a moment here. Okay, you said you thought they were from where? Chapter 2. Well, actually, they came out of the test bank for 1-1. Okay? And this is estimating, not doing. 2-1, you're actually finding it. Okay? 1-1, you're estimating it. And is it Elise?
Yes, sir.
Okay. I want to make sure I got it right. There you are. Okay. So, on your test, the first 2 are from section 1.1. The next 2 are from section 1.2. That's 3 and 4. 5 and 6 are from 1.3. 7 and 8 are 1.4. And 9 and 10 are from 1.5. Wait, no. I may have that. Yeah, I believe that's right. Okay. Yeah. All right. Now, there's something else I was going to say on that, and now I've forgotten what it was. Maybe it'll come to me later, and maybe not. I don't know. Sorry. Yeah, the first 2 are from section 1 in chapter 1. 3 and 4 from 2, 5 and 6 from 3, 7 and 8 from 4, and 9 and 10 from 5. Oh, here's what it was. Okay? If you want to find the limit and you want to use something from another section, if you can find the limit, that's all you have to do. I mean, I'm not saying you have to go back and use section 1.2 to find the limit if you know how to do it otherwise. Because now you do know how to do it otherwise, so any way you want to. But it was designed to be, the test bank intended that way. I'll let you find the limits any way you want to. Okay? Oh, and the 2 of you that just came in, did y'all get tests last time? Okay, both of you. All right. Okay. I think that's all we had on that. Any other questions? I did see you come in, and let me guess. Iwana? No. Taylor. Oh, sorry. All right.
So on the first two,
Yeah.
you do that by just getting secant lines that are closer to that point, like closer and closer, and then you just estimate
Yeah.
the
Yeah.
value.
Yeah, you can do that. That's what it is intended, or you can do it any way you want to if you can give me the slope approximate or exact there. And if you get really close, I mean pretty close, you'll get credit for it. If you get it right on the nose, I have to give you credit for that too. Okay. All right, good deal. Any others? Good questions, by the way. All right, this is on 2.1 then, and we had done the first few slides, and we had just been talking about secant lines and getting them closer and closer to finding the slope of the secant line, and therefore, as the limit of that will be the slope of the tangent line at one of the points. Okay, and this is what this graph illustration is showing. You can obtain more and more accurate approximations to the slope of the tangent line by choosing points closer and closer to the point of tangency as shown here. And what they're showing here is both of these delta x is getting closer to 0, but in one of these you're letting this point move closer to that one, and in the other you're letting the upper point get closer to the lower point. So one you're approaching the point from the left, the other you're approaching the point from the right. It doesn't matter as long as your delta x's are getting smaller. And of course the slope of a secant line is the slope of any line, delta y over delta x, but the delta y and delta x's will be on the curves at this point. Here's your alpha c. This is actually alpha, the point back here is c minus delta x, and this will be alpha c minus delta x. Okay? Whereas all these are c alpha c, the gray ones, as are the gray ones here. But over here, your point that you're estimating to is alpha c plus delta x. This is c minus delta x here. You can do it either way as long as the delta x is approaching 0. So this delta x it's closer to this point here. As this point here gets closer, making the delta x smaller, of course the delta y becomes smaller too. And you have that situation, 0 over 0, indeterminate form. In this case, you do have a limit, and that is the slope of the tangent line. Same thing as you bring the second point closer from the right. Your delta x is fairly small to begin with. Delta y is fairly large here. As you bring the point closer, your delta x is getting slightly smaller, but delta y is dropping like crazy. Okay? Delta x getting slightly smaller, delta y, and again, you get the same limit, the slope of the tangent line. Does that make sense? So it doesn't. Okay. Can I say anything to make it better? Probably not. Okay. All right. Okay. Now, we've been talking about it. Here now is your definition of a tangent line with slope m. F of x, f is defined on an open interval containing c. Now, when they say it's defined, that means the function is defined on this open interval containing c. There aren't any places where you have holes in the graph or you have asymptotes or anything else. It's defined everywhere on this open interval that does contain c. And if the limit as that delta x approaches 0 of your delta y over delta x, and as long as you don't have any breaks or extreme behavior in there, I'll tell you one other big piece of extreme behavior we haven't mentioned, but we'll get there in a minute. Then, if the limit of this, well, of course, the delta y, now this is using it from the right, is alpha c plus delta x minus alpha c. If you're coming from the left, this would be alpha c minus delta x. Whichever way will work. They're using the plus side, which is fine. Either will work. This is your change of y. Of course, that is your change of x, your delta x. And as your delta x gets smaller, because there's no breaks in the f, it's a smooth, that's the other feature, smooth continuous contraction here, the f's are getting closer together too. So as that goes to 0, the numerator goes to 0, and the limit as those two are going to 0, if there is a limit, that is your slope. And if it's defined on the open interval, I hate saying that because there are some exceptions for that, and I hate that they're saying it that way. But for right now, we'll ignore those. That will be your M. Okay, here's what. If the limit exists, then the line passing through that, the slope M, is a tangent line. Okay. They got away with the if there. I thought they say the limit will be this and it exists. If it exists, then that line, that slope will be the slope of the tangent line at that point. Okay. The thing I was fretting about is places like if you had, this is continuous and defined everywhere, if your function did like this and did like that. No, the slope of the tangent line is not defined at that cusp, corner, abrupt change of slope. It can't be defined there. So if the limit exists, then this is the slope. Don't worry about that one yet. We'll see it later. The slope of the tangent line to the graph of F at the point C alpha C is also called the slope of the graph. You don't always have to say of the tangent line. That's the slope of the graph at that point, at that particular point. And that slope is always changing as long as it's a curve. So a straight line, it doesn't change. But you see, here's the slope here, here's the slope here, here's the slope here, here. Changing all along that curve, okay? Always that tangent line slope is changing continuously on the curve. And that you can say is the slope of the curve or the slope of the tangent line at that point. Okay. So here's example 1. Find the slope of the graph of alpha of x equal 2x minus 3. Boy, that's going to be hard to figure, isn't it? Okay. When c is equal to 2. Okay, maybe they gave us an easy point there. You can apply the definition of the slope of the tangent line as shown here. I wish they hadn't shown all that. Okay. Let's just do it though. They did all the, well, not the hard part. They started it off for us. Let me get my pen set up. Sort of forget this for now. Okay, to find the slope of the graph there, it's exactly this is right. The limit as delta x approaches 0 of alpha of 2 plus delta x minus alpha of 2. Okay? Now, you're evaluating it at c equal 2, so what we had before, this was c plus delta x and c there. Plug in what c is, okay? And this is divided by delta x, okay? Now, what is alpha of c of 2 plus delta x? Here's your alpha of x. So alpha of 2 plus delta x would be what? It's not that hard. Everywhere you see an x here, plug in 2 plus delta x instead. So it would be, help me somebody. Okay. Yeah. We're trying to calculate what this is, which is exactly what was written here, but I didn't want you to see what they were doing. Okay. You're evaluating this. So you take your function, f. Alpha of x is 2, x minus 3. That means what? To do this function, take whatever's in here, multiply 2 times it, and subtract 3 from that. Now we're doing alpha of 2 plus delta x. So what would that be? 2 times, because it's times, 2 times whatever is in here, which is 2 plus delta x, good, minus 3. Okay, so that's what we write here. This will be the limit as delta x approaches 0 of, let's multiply that on out. I'm going to get ahead of them. Okay, what is that?
4 plus 2 delta x.
4 plus 2 delta x minus 3. Okay, minus, now you do the second part, alpha of 2. So what's your alpha of 2? 4, one more piece, 4 minus 3, right? Okay, which is 1. Okay. Over delta x. We still don't know that. Okay? Now, 4 minus 3 is 1. Minus 1 is 0. So now your limit as delta x approaches 0 is of 2 delta x over delta x. And I think I could do that one. What's that? 2. The limit is 2. Big surprise. Because what's the slope of a, what kind of equation is f of x 2x minus 3? The what? Oh, linear equation. And what do you know about linear equations when written in that form? What is this form called? Mx plus b. Right? What does b stand for? Y-intercept. Who cares about it? We're not right now. But what does the 2? What is M? Slope. That's a slope. Yeah. Big surprise when c is equal to 2, the slope is 2. When c is equal to 4,535,812, it's still 2. Okay, the slope is still 2. When it's negative 3 pi, it's 2. It doesn't matter everywhere the slope of that equation is 2, but we've just shown it for this value. Does that make sense? All right. Deal. All right. Now, I think they will, whoops, I didn't even turn the page, did I? Yeah. And that slope is 2. All right. Let me erase my scratch here. Any questions before I erase it? Yeah, feel free to ask. Sorry, my writing is so scattered and messy. Yes, I could write. Whoops. Okay. Why was my pen disappeared? Why is it doing this? There we go. I didn't write that in, but it's there. Okay. Any questions? Need it a little longer? Feel free to ask, folks, please. Better catch them now than later. Always. Ready to move on? Can I erase? All right. We'll see how they did it. They started it here, and they started exactly the same way we did. F of, this is your y1 minus y2, which is delta y, because f of x is always y, okay? And the larger x is 2 plus delta x, and the y1 is just 2. So you plug that into your function up there, 2 times 2 plus delta x minus 3, minus 2 times 2 minus 3, all over delta x. Now, they did it in a reasonable fashion. Sometimes they just skip all the math and give you the answer. This time they actually did it. 2 times 2 is 4, plus 2 delta x, minus 3, minus 4, minus is plus 3. Okay, folks? When you're dealing with these signs, be very careful on the signs. That's where you'll usually make your mistake. Not the hard part, not the calculus, it's the math. Okay, it's the simple math. Usually signs will trip you up more often than just about anything else. Okay, so what you notice when they write it this way, 4 minus 4 is 0, minus 3 plus 3 is 0. So you're left with just the limit is delta x approaches 0 of 2 delta x over delta x, and even I can get rid of those delta x's. And that's the whole key here. on your limits. If you can eliminate the thing that's going to 0, which we just did, then you see what the limit is. The limit of 2 happens to be 2. Okay, I'm glad they put that step in. Okay. Any questions? It's a lot neater than mine. Hopefully it's easy to follow, is it? Okay. See why they did every step. All right. So that's example 1. Oh, and here they even show the graph. Slope of alpha C is, and C is equal to 2. And if you remember back when alpha of 2 was 1, so 2, 1. So the limit of the slope there is indeed 2 because everywhere the slope of that line is 2. Looking at that, you can see the slope of the line is 2. Okay? At that point as well. Make sense? All right, good deal. Any questions? Okay. All right, they skipped example 2. So let's go back and we'll do example 2. All right. They did the easy one for you. Now let's see this one. Find the slopes of the tangent lines, the slopes, notice that plural, of the tangent lines, plural again, to the graph of alpha of x is equal to x squared plus 1 at the points 0, 1 and negative 1, 2. Okay, and they show you a figure. I'm not going to draw it. Okay, but cynic that I am, I want to make sure that this point is indeed on that line, on that curve. If it's not, then they've sent you on the fool's errand. You can't find the answer if it's not. So let's just check it and see. When x is equal to 0, is alpha equal to 1? Yes, okay. When alpha is minus 1, is alpha equal to? Yes, okay. So both of those points are on there. So yes, we have a legitimate problem to do. So how are we going to find the slopes? You don't think this is going to be the same slope at these 2 points? Why not? That's all. Okay, this is not a straight line. This is a parabola. And the odds of getting the same slope at any 2 points, I believe, are absolutely nil. Okay? Not going to happen. Okay? So, certainly these 2 points. Okay. So how would we do this? Certainly we want to use our limits, don't we? Because we love our limits. What would that be? Help me. Okay. Okay. Did you say as x approaches 1?
Change of x approaches 0.
Okay. Delta x, is that what you say? Okay, right. Delta x approaches 0. Of f of, give me the full range here without plugging anything in. F of x plus delta x minus alpha of x over delta x. I want the full Monty, you might say, not quite, but something like that here, and then we'll plug in the values. So let's first do it at this value. Okay, what would that be then? The limit of f of I always tend to forget to put the limit down here. Ugly, ugly, okay? If you plug in, what's your x value? 0. It'd be 0 plus delta x minus alpha of 0 over delta x. So the limit as delta x approaches 0. And what's 0 plus delta x? Okay, delta x. And if you plug that into f of delta x, I'll write that down. Okay, f of delta x minus f of 0 over delta x. Okay, we'll put one more step in there. And this will be limit as delta x approaches 0 of, and what is f of delta x? Help me, somebody. What would that be? Here's your f of x. What if I put a delta x in for x? What would we have? Delta x squared, okay, plus 1 minus, and what's f of 0? 1. We knew that. There it is, right up there. And that's divided by delta x, okay? Now, what do you notice you get here? The limit as delta x approaches 0 of, what happens here? To your 1's. They add to 0, right? And that leaves you delta x squared over delta x, which gives you what?
Delta X.
Just delta x, okay? Now, before, we got rid of all our delta x's, and that looked really good because you just had a number left. But really, all we're concerned with is getting rid of the delta x where it's giving us problems. That's in the denominator because you can't divide by 0. But in the numerator, no sweat there. What's the limit of that? Limit of delta x approaches 0, delta x. 0. Perfect. Okay? Now, okay, you can look at the graph in your book, if you got a book, if you don't. Oh, and by the way, I meant to say this. The guy finally got back to me from Cengage. He said, yeah, I got all your courses set up. Oh, I had one question about this one, not this course, differential equations. I was giving him all the information. So I gave that to him, but he said, I set the rest on, tell me what you think. Well, I looked. I only had 4 courses. I had asked for 7, and this was one he didn't have. So hopefully today or by Wednesday, he will have responded and given me the thing. Is anyone being held up because you don't have the code? Can everybody access your book and whatever else you need? Okay. So it may not matter to any of you, but once you get the code, you can use WebAssign if you want to. And it does have good tutorial and other things in it, so just wanted to let you know. All right, so we've done this. If you look in your book, you'll see, sure enough, at 0, 1, what's the slope of that line? You'll have to look in the book. Okay, I guess I need to draw it for you. Okay. All right, this parabola looks like this. It's the normal parabola that goes to the origin and goes up either way. This, because it's a vertical translation by 1 up, it's a parabola like something like that. I don't draw very neatly. Okay, and here is your tangent line. What's its slope? 0. Very good. Well, that one was easy, sort of. Let's do the 1, -2. Yuck. Okay. So I'm going to go through and erase some things. Is that okay? Delta x approaching 0 is still the same. That's still the same. But now your x is not 0, but -1. So I'll erase those. And that'll change this and that. And probably everything here except the denominator. And probably most of that too. Okay. So let's see what we've got. When you plug in x equal negative 1, this becomes a minus 1 here and a minus 1 there, right? And I think we could skip this step here altogether. And let's go straight to down here because we're going to need the room. Okay. This is a lot easier for me to do than for you, but that's all right. I'm the boss. No, I'm okay. All right. So what is f of x plus delta x, or negative 1 plus delta x? What would you do with that? I think I may put this in. What would that be? Okay, a little louder. I hear something, but I can't make it out. Okay, yes. We'll put our negative 1 plus... No, we don't substitute the 0 yet. Not yet. Okay. Negative 1 plus delta x is we plug into this thing. So what does that give you? Negative 1 plus delta x squared plus 1 minus, now this one we just plug in negative 1. And we already know the answer to that, don't we? What's that? 2. Okay. All right. So let's square this one first. What is negative 1 plus delta x squared? Anyone do it right off the top, or do you need to go off to the side and do a foiling or something? Let me know. Anybody? 1. Okay, I'll buy that one. Minus delta x, is that what you said? I think it's minus 2 delta x, isn't it? Okay, here's the rule for squaring a binomial. Square the first. Did that right. Twice the product of the two. Remember? Because you have a outer and inner that are the same, so that's what minus 2 delta x. Okay? Next. Plus delta x squared. I'm going to put that in there so you don't confuse it with delta x squared. And then we had a plus 1 and a minus 2, right? Or we could have just made that a minus 1. Doesn't matter. What do we have now? What do we have now? Here's a 1 plus another 1 is 2 minus 2 is 0. Those go away. Didn't know you'd be doing such high level math today. 1 plus 1 is 2, right? Okay, good. All right, so what do you have left? This entity right here, right? And what do you notice about that?
Factor out a delta x.
Factor out a common factor of delta x, and that leaves you what? Minus 2 plus delta x. And then this is divided by delta x, and what good news do you see now? You can lose the delta x in the denominator. That's what was giving you problems. So now we can do that limit, and what is that going to be? Negative 2. Because as delta x goes to 0, delta x goes to 0, and your numerator gets closer and closer to negative 2. All right, now, if we had drawn our graph anywhere decently, which I'm not claiming to have done, at negative 1, you're up here at 2, okay? And what's the slope of that line? Well, it sure looks like it's negative to me, and if we had drawn it properly, you would see it is indeed negative 2. All right, make sense? All right, good deal. Now, for some reason, they did C's and F of C's and carried that all the way through and then went back and plugged in C is equal to 0 and then C is equal to negative 1. That enable them to only do the limit once. So if you like doing it that way, you can get your answer and then plug in c equals 0, c equals -1. I didn't think about doing that, but certainly legal to do in most states anyway. All right. Any questions? All right. Now we move, if there are no questions, y'all okay with it? Any questions? I'll answer them. I'll try anyway. Got any? Okay. Then let's move on to this. Nope, that was example 1. Now, back to where we were before. The definition of a tangent line to a curve does not cover the possibility of a vertical tangent line. And you can have those. For vertical tangent lines, you can use the following definition. If f is continuous at c, then the f of c plus delta x minus f of c over delta x. If it's a vertical line, it's an infinite slope. But can anyone tell me if that vertical line is infinitely that way or that way? Which way is it going? You know, it's sort of hard to say. So either one of these. Usually what it's going left to right, if it was increasing, then it'll be a positive infinity. If it was decreasing, then it'll be a negative infinity. But either way, it's undefined. So I don't like using a symbol to represent undefined. Let's just call it undefined. Then the vertical line, x equals c, passing through c, f of c, is a vertical tangent line, and that line has no slope. Okay, period. This kind of a curve, I know it probably has several different names, but when I see it, I think of the name called the logistic curve. And this is, you use a lot in modeling diseases and things like this. At low exposures, you generally don't have any disease, but then once you get a few exposures in a population, more people will start getting the disease. And when the disease gets really out of control, the rate at which more people are getting exposed actually approaches infinity. But then as more and more people get exposed, then fewer and fewer have not been exposed, so you level off until the whole population has been exposed. So you start at 0. That is what I call a logistic curve. I'm sure it has other names and other context, but my wife's an epidemiologist, so I have to think in terms of diseases or I get in trouble. Okay. So anyway, that's an example of all along here the slope's increasing incredibly rapidly, and then at some point it starts decreasing again. But it never became 0. But it decreased very, 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 very slowly. So this one you would say was infinite at that point, or just undefined. It was infinitely large. It kept getting larger, but then slowly started decreasing. At that point, though, it wasn't defined. Okay. Any questions on that? Okay. Later, hopefully in this course, we'll start naming what kind of special point that is. Some of you may already know. Okay, when the domain of f is a closed interval a to b, okay, you can extend the definition of a vertical tangent line to include endpoints by considering continuity and limits from the left, right, and right from x equal a and from the left to x equal b. Okay. Why do they say it's a tangent line problem? There's no problems with it, are there? Never mind. Okay. All right. That's all they say right at the bottom of the page. Now let's talk about the derivative of a function. Believe it or not, we have been talking about it. We just didn't call it that. The limit used to define the slope of a tangent line is also used to define one of the two fundamental operations of calculus, differentiation. The definition of derivative of a function, boy, does this look like a surprise. The derivative of f at x, and there's a couple of different symbologies we use. This is called the prime notation. F prime, that means derivative of f at the value x is the limit as delta x approaches 0, no change there, of f of x plus delta x minus f of x divided by delta x. Exactly what we started off with in our tangent lines. Provided the limit exists. If this was one of those infinite limits, no, it won't exist. Okay? If it's one of those, and we'll see a couple of other examples, like the function doesn't define there, nope, it can't be. And there will be other cases like I pointed out to you before. Provided the limit exists. For all x for which this limit does exist, f prime is a function of x as well. Now, if this was a linear function here, you can say it's a function of x, but it's going to be a constant, which is a function of x. F of x equals 2. That would be perfectly fine. Okay. Be sure you see that the derivative of function x, they just said this, also is a function of x. This new function gives the slope of the tangent line to the graph at every point x alpha of x. So since it depends on x as well, it's a function of x. Provided that the graph has a tangent line at that function. The derivative can also be used to determine the instantaneous rate of change. That's why Newton did it. He needed to know, for instance, those planets, when they were going around the sun in an elliptical path rather than a circular path, what was their speed at velocity at any point there. Not just the average, what was it? Instantaneous rate of change, or simply the rate of change of one variable with respect to the other. One I was giving with respect to time, it could be anything. The process of finding the derivative of a function is called differentiation. A function is called differentiable at x when its derivative does exist at x, and it is differentiable on an open interval a to b when it's differentiable at every point in that interval a to b. But notice this is open interval, which means generally it's kind of hard to define differentiability at the endpoints because you don't know what comes next, okay? So we usually leave it open. All right. Bunch of words. All these graphs are all the PowerPoints are online if you, on Blackboard if you need to see these. If you don't have a text yet, you can get these there. But if you want to write them down, I'll give you time if you need it. Anyone need it more? Okay. So in addition to f prime of x, which we call just the prime notation, which is called f prime of x, okay? Other notations are used to denote the derivative of f. The most common are these. And these are all. As the prime notation. This is called the Leibniz notation, dy dx. Now, what do you notice about this? It seems sort of familiar, maybe. The deltas became d's. As delta x approached 0, it was approaching delta x. And incredibly small incremental change in x. And as that was happening, because it was an indeterminate form, the delta y was also approaching in a limit delta y, dy. Okay? So that's the new form, dy dx. Okay? It may sound like it, but I'm really not making fun of Indian and Indian speech. We have some really good friends who are Indians, and I tutored all three of the boys when they were at various points in high school and college. And Samuel, the oldest, I guess this is how they said it in India. He said, dx. And when he first said it, I said, what? dx. And he went d by dx of whatever function it was. So d by dx of f of x. And now I can't help but say it like that. It's d by dx of f of x. Okay? And here's one that we really aren't going to use a lot now, but you will see it show up later in math if you go much further. this is the derivative operator, which is this thing right here, d to the x, okay? And the x here tells you what's on the bottom, and the y tells you what you're operating on. You're operating on y. So dy dx, the f of x dx. Here's another one they didn't put. df dx. That is just the same as this. If y is equal to f of x, they'll sometimes say df dx. I don't know why they left that one off here. And this means this operator, d to the x, with x being in the denominator of y. Or of f of x. You could put that in there too. These are all different notations for the same thing, your derivative. The notation d dy dx is called derivative of y with respect to x, or simply dy dx. Okay? Rather than by in there, dy dx. Using the limit notation, you can write any one of these is equal to the limit of as delta x is approaching 0 of delta y over delta x, which of course was the limit that we had back on the previous slide of f of x plus delta x minus f of x, that's your dy, over delta x, or f prime of x, or any of these others you can write here or here on either side. These all mean the same thing. And why we have so many, I'm not really sure. And none of these are Newton's form. Newton used dots, okay? And that really confused people. Some people started calling it the fly speck, because what if his paper had a random speck of, darkness in it? Is that a derivative or not? It was hard to tell. So unless your random speck just happened to be placed right there, I guess you could confuse those two, but any of those notations will work. So let's do example 3. To find the derivative of f of x equal x cubed minus 2 plus 2x, use the definition that they give here, and I'll let them write this down. Okay? So what would you write next? The limit as delta x approaches 0 of, now we got some work to do. Just tell me what to write here. Here's your f of x. Whatever is in the parentheses, you're cubing it and adding twice that. What's in your parentheses here? X plus delta x. So you take that, x plus delta x, and you do what to it? Cube it and add twice that. I can't write x plus delta x. Okay? Minus, what do we write next? This thing right here. X cubed plus 2x. That is your f of x. Okay? And that's divided by delta x. Okay. Now we've got to cube a binomial. There are a couple ways you can do it. Write that as x plus delta x times x plus delta x squared, and you know how to do a square, right? Or if you really are lazy, have any of you heard of Pascal's triangle? I probably shouldn't introduce it now, but why not? I'm lazy, okay? Start with a 1, and then do another one and another one, and then do another one, okay? But now, in between each one, you add these two together. 1 and 1 is 2, and then you do another 1. And guess what? This is, I'll leave it, a plus b. These are the coefficients of a plus b to the 0th power. Because what is a plus b to the 0th power? Nope. 1. Anything to the 0th power is 1, and there it is. To the 1st power, it's a plus b. Those are the coefficients, a plus b, right? Okay. To the 2nd power, and you probably say, why didn't you show us this one before? Okay. What was that? A squared plus 2ab plus b squared. That's coefficient 1, 2, 1. Anyone want to hazard a guess what the next coefficients will be? 3, 3, 1. Okay? Now, you have to figure out what the variables would be. You got x's and delta x's rather than a plus b's here. So this will be the limit as delta x approaches 0. That's the easy part. Okay, we're going to cube this, so that'll be x cubed with a 1 as a coefficient plus, what next? Three x squared. Now, your first one, you decrease by 1. Your second, you increase by 1. These are your powers. Okay, so that'll be delta x. X squared delta x. Okay, I'm probably not explaining this too well, but that's how your exponents go. Next coefficient is 3. Decrease the x by 1, leaving it 3, 2, 1, okay? But increase your delta x by 1, which is squared, plus 1. I'll do the 1. I won't write it down, though. Decrease the x by 1, you get x to the 0. That's still 1. Delta x cubed. All right, you've just done Pascal's triangle. This is a binomial expansion. Okay? Whew. Can I erase it now? I don't know if that was any easier. You could have... Oh, it didn't erase, did it? Okay, here we got it. And you can carry that as many... You can carry that triangle, expand it as long as you want to. Okay, that's the cube part. We still got the squared part to go. What's that? Plus 2x, it's not squared, 2x plus 2 delta x. Now we can subtract, can't we? Minus x cubed, last, minus 2x. Whew. What a numerator over the poor little old denominator delta x. What would you suggest we do now? Combine like terms, okay? There's an x cubed, but there's a minus x cubed. They disappear. There happens to be a 2x and a minus 2x. They disappear. Or add the 0, which is the same as disappearing. And all the rest of your terms have a what in it? Have a delta x in it. So let's go on and factor that out. Here's a delta x we're going to factor out, which makes us really happy. So this loses that one. This will lose one of those. This loses only 1, leaving you 2. I probably should put that in parentheses. This one will go away. So what do we have left? 3x squared plus 3x delta x plus delta x squared. And I think all the rest of them disappeared. Oh, so close this off. And that's all over delta x. And what's the good news here, folks?
What happened to 2 delta x?
The what? Did I leave one off?
The 2 delta x.
Oh, what did happen? Oh, yeah, plus 2. I wiped out the delta x. I thought I wiped out the 2. You're right. Okay. So I shouldn't have really wiped out the delta x's up there, but I thought it would make it clearer and it made it more confusing. Okay. What I did, I took out the delta x, which left 3 delta x squared, 3x delta x squared plus 2. I forgot that one. That delta x is the one I pulled out here. Okay. All right. Now, what's the good news? Delta x over delta x is 1. It divided out to 1. So now we can take a limit. Can we take a limit of that? As delta x approaches 0. What does 3 3x delta x go to if delta x is going to 0? That goes to 0. How about this one? It goes to 0 really fast, but it's still going to 0. So what are we left with? 3x squared plus 2. Fantastic. There is your limit. There is your derivative. Derivative f prime of x for that function f is 3x squared plus 2. And I see Dawson shaking his head because he's already had this. He knows an easier way to do it, don't you? I'll just shut up. Never mind. Okay. No. As Chuck, I'm sure does too, and Bill. Several of you probably do. Okay, but sure enough, that gave you the right answer. All right. That's how I scratched through it and did it. Let's see how the book did. Can I erase this? Yay or nay? Okay. First thing they did was expand that and do just like we did. Limit is delta x approaches 0 of x plus delta x cubed plus 2 times x plus delta x minus x cubed plus 2x in parentheses over delta x. And then when you expand that, and look, they didn't show you how they did it. They just said, here's the answer. But it's x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. Just like we did with Pascal's triangle, it works here. Plus 2x plus 2 delta x minus x cubed minus 2x all over delta x. Okay? Now, they didn't show you how, but you see the x cubed and the minus x cubed add to 0, and the 2x minus 2x adds to 0, leaving you with this thing, which every term in it has a delta x, which they just wrote down for here, which probably was the safer way, because they didn't make a dumb mistake by forgetting that last term. But there is your what's left. Now that's pretty obvious. Each of those in the numerator has a delta x, so let's factor it out. And that's the limit of delta x equals 0 of, and I wish it had been at the bottom here, the delta x out here, that left the 3x squared plus the 3x delta x plus delta x squared plus 2 over delta x. Delta x is divided out to 1, and that then leaves you a limit of 3x as delta x equals 0 of 3x squared plus 3x delta x plus delta x squared plus 2. Of course, the two middle terms, as delta x gets close to 0, 3x delta x, no matter how big x is, as delta x goes to 0, that's going to be heading towards 0, and delta x squared definitely is going to 0. So this is just 3x squared plus 2. Right? Good deal. That was example 3. They're skipping examples 4 and 5. So you want to go back and pick those up? Of course you do, don't you? Okay. Because usually these are, as someone's already pointed out, in a roundabout way, here is example 4. F prime of x, find f prime of x for f of x is equal to the square root of x. Okay. Quit grinning. Okay. All right. Then find the slopes of the graph at 2 different points. So let's first find our f prime. I hate having to do it this way, but we're going to do it this way. F prime of x is going to be in limit form, what? The limit as delta x, this should not be new, approaches 0 of f of x plus delta x minus f of x over delta x. Not liking this one too much, are we? What does that numerator become? I really want to leave off these limits, but I'm afraid if I do, I'll forget to put them back in. Or I'll have to cram them in. They look so ugly. So what is f of x plus delta x? the square root of x plus delta x minus, what's f of x? The square root of x, all over delta x. Can we possibly do anything with that ugly looking difference quotient? Huh? What comes to mind from our last chapter? Rationalize the numerator, not the denominator, the numerator. And what do we mean by rationalizing it? Multiply it by the what? The conjugate of the numerator, which would be, let me just go off to the side and do this. I don't have room over there. X plus delta x minus the square root of x over delta. Gag. Okay. Okay. And how do we rationalize that? What's the conjugate of the numerator? The square root of x plus delta x plus the square root of x. But if you multiply the numerator by that, what must we also do? The denominator by the same thing, x plus delta x plus square root of x. Okay. Now, what happens to that numerator? You get what? You're foiling it, right? What does that first one give you? X plus delta x. Okay? Now, if I did my outwards and my innards, okay, you'd have this, that's a plus, and that a minus, and they're exactly equal to each other, right? So those add to 0, which is very nice. Then when you do your last, what do you get? Minus x over, let's leave that, please don't multiply it through. Let's just leave it in this form. Square root of x plus delta x plus square root of x. Okay. Now, what do you notice about that numerator? Now, it has the limits in front of it. Okay? I'll go back and put them in later. What do you notice about the numerator? X's add to 0. So you have the limit, I'm writing them in now, of, as delta x goes to 0, of delta x over delta x, oh nice, times the square root of x plus delta x plus the square root of x. And what do you notice happens here? Yay, we get rid of your delta x's. That goes to 1, and now we have the limit as delta x approaches 0 of numerator is just a 1, the denominator is the square root of x plus delta x plus the square root of x. And can anyone tell me what that goes to as delta x goes to 0? Well, what does this go to as delta x goes to 0? Square root of x plus square root of x is 2 times the square root of x. So we have 1 over 2 root x. Okay. And that indeed is the limit. I really don't like this form, and you'll seldom see me use this form anymore. Later we'll use a different form, which I find much more satisfying when you're doing derivatives. But in this way of doing it, this is perfectly good, and that is indeed your answer. Now, that's the first part of your answer. It said, find f prime. This is f prime. F prime of x. When f of x is that. Okay? So, the second part said, find the slopes of the graph at the points 1, 1 and 4, 2. Okay? At 1, 1 and 4, 2. That was a comma, folks, but it became a 2. Okay. Duh. Now, of course, cynic that I am, I want to make sure these 2 points are indeed on this curve. And when x is equal to 1, what is f of x? 1. And when x is equal to 4? 2. Yeah, those are on there. So let's find out what the slopes are at those 2 points. So f prime of 1. The x value here would be, what is f prime? 1 over 2. Okay? So it's 1/2. F prime when x is equal to 4 would be 1 over 2 times 2 is 4, 1/4. So the slope at x equal, okay. Now let's remind ourselves what the square root function looks like. Ooh, that's messy. It's half of a sleeping parabola, okay? Put a parabola on its side and do the top half of it. So x equal 1, let's just say is right about in there. Sure enough, well, I did it too far up. About there, the slope is 1/2. When you get out here to 4, it's only 1/4. Now that's really qualitative, not quantitative here, but you see the slope is decreasing as it goes. What's the slope at 0? Not defined because you put a 0 in for your x, you wind up dividing by 0. And sure enough, that's an infinite slope there. That being half of a sleeping parabola, that would have been the vertex. The slope of the vertex when it's upright was 0. On the side would be vertical. No, can't help it. Okay. That was not part of the problem. Okay. Any questions? Let's make sure they got the right answer in the book. Sure they did. Excellent. Good for them. Any questions? All right, let's go to example 5. And I forgot to bring my watch in. Can I depend on some of you to tell me if I've gone over? Y'all are so kind. Okay. So how much we got? Second? Oh, great. Okay, we got plenty of time. All right, so let's do example 5. I know some of you are itching to get to the real derivatives, right? Not these limit messes. Okay. Finding derivative of a function. Oh, that's creative. That's what we've been doing, isn't it? And by the way, this one says see larsoncalculus.com for an interactive version of this type of an example. So you certainly can do that. So here we find the derivative with respect to t of the function y is equal to 2 over t. Okay. Anyone want to suggest some places that probably won't have a derivative? T equals 0, because the function is not defined there. How in the world could it have a derivative there? It can't. Okay, so yeah, don't even try it. Okay. So if you want to call this an f of t, what would then be your derivative? And I'm going to use one of the other notations. Sometimes they'll call this y prime. Oh, heaven forbid, but they do call it that. Or f prime of t or y prime of t. There's lots of different things. What would you suggest that would be? The limit as... Can you do it if you don't have an x in there? Yeah, it's delta t approaches 0. Yeah, it's just, really, that x is a dummy variable. You can put anything in there. Stickman if you wanted to, you know, whatever. Limit of, let's write it out. F of t plus delta t minus f of t over delta t. Perfect. Okay. Now, let's figure out what those things would be. This y prime would be equal to the limit as delta t approaches 0 of, what is f of t plus delta t? 2 over 2 plus delta t, perfect, minus 2 over t over delta t. Uh-oh. What are we going to do here? Okay. Again, can I leave off the limits for now and we'll come back and put them in later? I just hate writing those limits all the time. What would you do if this was a problem given to you in algebra? What would you do? Here's yes, you have a fractional form in the numerator. Let's use least common denominator. And what is your least common denominator in the numerator? Anybody? Help me. I'm up here dying by myself. What? Least common denominator? T times t plus delta t. T times t plus delta t. Okay. Now, what did I have to multiply this denominator by to get that least common denominator? T. Well, if I multiply the denominator by that, I better do what? Multiply the numerator by it too, so that gives me 2t. And what did I have to do over here? Multiply that denominator to give me the least common denominator. T plus delta t. So I better multiply that by t plus delta t, right? And this is all over delta t. Okay. Let's fiddle with the numerators. We've got the same denominator, so let's put it over t times t plus delta t. Okay. That's our common denominator. What's your numerator here? (2t) minus, and what's the numerator here? Multiply through. 2t minus 2 delta t. Okay, very good. Over that, and that's all over delta t, right? But what magic do you see happening in that numerator, of the numerator? The 2t minus 2t adds to 0. So now we have a minus 2 delta t over a t plus, t times t plus delta t over a delta t. Get out of there. Okay. That should be a t. It looks like an x. Okay. Now here, nice. The delta t's disappear. So let's put our limits back in. This now is the limit as delta t is approaching 0 of minus 2 over t times t plus delta t. Is that not right? And what does that give you as delta t approaches 0? That goes to 0, but you have a minus 2 over t squared. Minus 2 over t squared. And later, I will not like to write it in that form, but I will go back and change it to that form. That's indeed your derivative of that function. The derivative of the function at any value, except t equals 0. But we knew we couldn't do that because the function's not even defined there. Okay. So for any other t that the function where the function is defined, yep, you can find this derivative right there. And guess what sign that derivative will always be? Negative, which means wherever you are, it's a decreasing function. So over here, it happens to be going like this, and up here, it's going like this, okay? Always decreasing. I didn't tell you how I knew that, but it does. Always decreasing. Net derivative is always negative. Oh, we didn't talk about, yeah, slope of a line at any point is going to be negative. Okay? Any questions? All right, that was example 5. Now we're ready for, differentiability and continuity. Okay? You'll see that these are related, but they're not anywhere close to the same. The alternative limit form of a derivative is useful investigating the relationship between differentiability and continuity. And I don't think they've shown us this before, but really it is indeed true. The derivative at some value c is the limit as x is approaching c of the change of the y values as x is approaching c, it's getting closer and closer to c, as x minus c, x is approaching c. So the difference of the numerators, delta y's over delta x's, as x gets closer to c, this is going, that's your delta x is approaching 0, and this is your delta y is approaching 0. Okay. Provided that limit exists. Okay? That to be the case. So here's basically what it's saying here. Here's your c, and here's some value for x. You can have the x over here or here, but somewhere on the interval where this function is defined, both x and c must be defined as well. Okay? C is some fixed value, x is variable. Okay? And the way they have it written here, here's your alpha c is right here, and alpha of x is right here. And as x gets closer and closer to c, this time the x is pulling closer. Oh, this is fixed. That's a constant. Okay? That's why they named it c. Okay? As x gets closer to c, then this alpha of x is going to be moving down the curve, and sure enough, delta y, alpha of x minus alpha of c, is going to be closer and closer to 0, and the x minus c is closer and closer to 0. So this is saying the same thing as your delta x approaching 0, delta x here. Okay? It's saying the same thing, same point, same everything. Okay? Now, note that the existence of the limit in this alternate form requires that one-sided limits, either x approaching c from the left or right, that's what I was saying, x could be over here or there. So if x is approaching c from the left, then you have, everything going on the lower end here, has to be lower in this problem, or from the right is approaching c from there. So this has the limit as x is approaching c from the left-hand side of this. And notice both of these are negative. Well, in our example, both are negative. This is definitely negative then because x is less than c, so this would be a negative. But then whatever sign this was, this is going to be the opposite of that as they're coming in there. And this is just like we thought. They exist and are equal. The existence of a limit in this alternate form requires that the one-sided limits must exist and must be the same. All right. Those one-sided limits are called the derivatives from the left and from the right, respectively. Okay? It follows that f is differentiable on the closed interval from a to b This is not well written at all. When if it is, either the if is out of place or the when is out of place, but I don't think both of them need to be there. Yeah, the if should not be there. Okay. When it is differentiable on the open interval a to b, okay, and when the derivative from the right at a and from the left at b both exist. Okay? And I guess somehow this says it better than if we'd have done it the other way, but it seems like it would still been, the wording would have been exactly the same here without the if in there. Okay. When a function is not continuous at x equals c, it is also not differentiable at x equals c. This greatest integer function, remember, it's not continuous at the integral values. So therefore, it's not differentiable at the integral values. At x equals -1 or 0 or 1 or 2 or 3 or -2 or any integer, because the derivative, the function's not defined, it's not continuous there. So how could the derivative? Even though the derivative at every point other than that is 0. always 0, derivatives here and here are not 0 because they're not, you have a huge jump there. Now this isn't the only case, but this is one case. So obviously, if f is not continuous, it's not differentiable at that point of discontinuity. Okay? They just use x equals 0, but any of the integers would be the case. Okay? So if it's not continuous, it's going to be really hard to be differentiable at those points of discontinuity. In between it can be, but not at the points of discontinuity. Okay? Now, you can verify this by observing that the limit f of x minus f of 0 as x is approaching 0 from the left, and x limit of that from the right. So from the left, this would be the absolute value of x. This would be just 0. Greatest integer in x. And as x is approaching 0 from the left, but not at 0, this is 1. Okay? 1 minus 0 over 0 is not defined. I don't like to call it infinite. It's just not defined. But as you approach from the right-hand side, the limit of this is 0 as you're approaching from the right. This is 0 minus 0 over x approaching 0 but not equal to 0. That numerator is 0, so that's an indeterminate form, and that one does happen to be 0. The slope here is 0, and as you approach there, it stays 0. As you approach here, it's not even defined there. It's easy to get so bogged down in these really obscure examples of when it's not. You can almost forget that most functions aren't like this. Okay, that is possible for a function to be continuous at x equals c and not differentiable at x equals c. So from the right, it is continuous coming in from the 0 from the right, but it's not differentiable. Okay. Here's another one. This one is continuous everywhere, but it's not differentiable here. This is the absolute value. And they didn't have to say x minus 2. It could have been x. All that does is shift it from the v from being here to over here. That's just a horizontal shift to the right. Okay? And the reason it's not continuous there at x equal 2, it's continuous there but not differentiable here because the derivative as you're coming in here is minus 1, and derivative as you're going out here, coming in here, that's plus 1, and they're the twain to meet. No matter how close you get to x equal 2, it's still going to be two completely different derivatives coming from the left and right, so therefore not differentiable at x equal 2, even though it's continuous at x equal 2. So basically, differentiability implies it has to be continuous, but being continuous doesn't imply it has to be differentiable. And again, there's just a few functions, this being one, that's going to be the case. Okay? Most of the functions you'll deal with, unless they have discontinuities or weird behavior like this, and what we call this, continuity is 1/2. What this is not smooth. Okay? It's pointed, it's jagged right there. Okay? A function has to be continuous and smooth for it to be differentiable. This is continuous but not smooth. We haven't gotten to that yet, but we will. That's a graph with a sharp turn. This was example 6. Yeah. I didn't realize we were doing an example here. And see LarsonCalculus.com for an interactive version of that type of an example. And basically, I've just given it away. What you do, you take the limit as you come from the left, and the limit as you come from the right, and from the left. As x is approaching 2 from the left, x minus 2 is going to be negative, right? X is approaching 2 from the left. But this is always going to be positive. But they're going to have the same value, but that's going to be a minus 1. But if you're approaching 2 from the right, then this is x minus 2 is a positive value because x is greater than 2 coming in from the right, and its absolute value is the same as its value is the same as its absolute value, so that's going to be a positive 1. Positive 1 from the right, negative 1 from the left, and those limits are different, so the derivatives are not different. They're not equal, so it will not be defined. Derivative is not defined at x equal 2, or as x approaches 2. All right, make sense? Okay. So if f is not differentiable at x, so f is not differentiable at x equal 2, the graph of f does not have a tangent line at the point x equal 2, or at 2, 0. That point is on the graph. It's a continuous point on the graph, but it does not have a tangent line. A function that is not differentiable at a point at which the graph has a sharp turn or a vertical tangent line. So here is your theorem 2-1. Differentiability implies continuity. I already sort of said that. If f is differentiable at x equals c, f has to be continuous at f x equals c. But does this go the other way? Not necessarily. This is one of those if, then, the arrow points this way only. If and only if, then it points both ways. This does not point both ways, it only points that way. The relationship between continuity and differentiability is summarized below. If a function is differentiable at c, then it has to be continuous at c. So differentiability implies continuity. It is possible for a function to be continuous at x equals c, not differentiable at x equals c, so continuity does not imply differentiability. The arrow cannot point that way in that statement. Okay. Whoa! That was the last. However, there is an example 7. Ooh, that's not much room to write. Let's see. We'll write here. We'll just have that in the middle. Here's a function. F of x. How are we doing on time now? 3 minutes? 2 minutes? It's 2 minutes. I don't know. I don't think we're going to make it, do you? Okay. So we'll start next time with example 7. However, we got a lot of homework exercises that we can play with. I would say, good news here, right? Number 5, it's at calcchat.com. Do number 7, it's at calcchat.com. It's got 4 pieces to it. Do any of the odds, 9 through 13, they're all at CalcChat. 11's at CalcView. Do any of the odds 15 to 27, they're all at CalcChat. 17's at CalcView. Do any of the odds 29 to 35, they're all at CalcChat. 31's at CalcView. Do any of the odds 37 to 41, they're all at CalcChat. 37's at CalcView. Do any of the odds 43 to 47, they're all at CalcChat. Then you can explore doing either 49 or 51. I don't know for certain they're at CalcChat. They should be. So if you want to give them a shot, you can. You sort of have to make up your own functions and do stuff. So if you don't want to mess with those, you don't have to. But they're nice to think through. Try to do 53. It should be at CalcChat. Either 55 or 57. They both should be at CalcChat. 57's at CalcView. Do 59, it should be at CalcChat, and try to do 61. It should be at CalcChat. 63 should be at CalcChat. 65 should be at CalcChat. Now, these are suggesting that you use a graphing utility to do it. These are pretty simple functions, most of them. So I think you can do it without that. Okay? And 67 should be at Calc Chat. Okay? You can do any of the odds 69 to 75. They're all at Calc Chat. 69 is at Calc View. You could do either 77 or 79. They're both at Calc Chat. 77 is at Calc View. You can try doing 81 or 83. They're at Calc Chat. 85 or 87. They're at Calc Chat. 87 is at Calc View. Try doing 89. That should be at Calc Chat. And 91. Okay, there's a couple of true faults. You won't see them like this on the test, but they're really still pretty good to think through. 93 and 95, they should be at Calc Chat. And then 97 should be at Calc Chat. That will do it. And if y'all get all these done, we're going to have another day or so of it. So. Anyone making decent progress on the test? Good. All right. We'll see you then on Thursday. Wednesday, I'm sorry. I'm trying to move the week along here.
When it says you can get.
Oh, fantastic topic.
Oh, really?
Yeah.
Okay, like, so do I have to go in depth on, like, the theories, or, like, just basically do a typical paper about them?
You can do it either way you want.
Okay, that's what I thought. Okay, all right.
Good deal.
I'm gonna regret this, but
Oh, I don't think you will. Oh, I'm sorry. When did you come in?
I stuck here.
Okay.
We were up at the board, you didn't see me come in.
Oh, I'm sorry. Let me see. Iona? Iona. I have it marked that. Iona. Okay. Got it. Perfect attendance today. I'm glad you made it. Good deal. Thanks for telling me. One reason I was asking you about your major, has anyone suggested anything to you, leaked anything? I'm pretty sure you're going to be recommended for honors and award coming up in April, I think it is. So wanted to give you a little heads up. Not a big deal, but the thing is we've got to decide whether we do you as engineering and math, because they have you in the books as pre-engineering. And we have an award for each, and they're exactly equivalent. So, but we don't know. Do you have a preference which you would be considered as?
I mean, that's weird that it's not officially mathematics, because I know like my degree plan and everything changes mathematics.
Right, I thought it had, but she may have been pulling the data from the beginning of the term. I don't know. Because didn't you just change this term? Yeah. So.
I mean, either one is fine.
Okay. The awards are exactly equivalent. So. Yeah. And I recorded that, by the way. Okay.